Section 9.1, Solving Differential Equations. A differential equation is an equation involving an unknown function and one or more of its derivatives. You can think derivative equation, and this is in contrast to, say, algebraic equations, where here our unknown is a function, and in algebraic equations, often the unknown represents a numerical value. The order of a differential equation is the highest order derivative that appears in the equation. Let's look at some examples. If you had f prime of x equals 3 times f of x plus 4, this is a first order equation in the unknown f of x. On the other hand, dy over dt equals sine t plus y is a first order differential equation in the unknown y, or y of t. And lastly, if you had y double prime plus 3y prime plus 2y equals e to the minus t, that's a second order differential equation in the unknown y of t. In this section, we focus on solving first order differential equations which are separable. And I'll show you what I mean by separable. Let's just jump in with an example. Let's solve the differential equation dy over dx equals x squared y for the unknown function y of x. That is, we're looking for a function y of x that when we substitute it in to the left-hand side wherever we see a y and the right-hand side wherever we see a y, we'll get a logically true statement. First, what we want to do is try to separate our dependent variables and our independent variables. Here, our independent variable is x, our dependent variable is y, and we would like to separate these multiplicatively. In other words, can we get everything involving y on the left-hand side and everything involving x on the right-hand side? Now, even though this isn't a fraction, we can think of these dy and dx differentials. Formally, we can treat them as fractions and just say, let's multiply both sides by dx and let's divide both sides by y. Then we get this form. This is called the separated form because the dependent variables, along with its differential, is separated from the independent variable along with its differential. And if you can put a differential equation in this form, then we call this a separable differential equation, and this is the separated form. Now, the nice thing about being able to put a differential equation in separated form is we can just anti-differentiate both sides. Notice this is an antiderivative with respect to y. This is an antiderivative with respect to x. If we do this antidifferentiation, on the left we get ln of absolute value of y. On the right we just get x cubed over 3 plus a constant. Now, if you notice, I did not put a constant on this side and on this side. Imagine if I did, if I put like a plus constant, plus c1 on the left-hand side as the constant of integration, and I put a plus c2 on the right-hand side. Well, then I could just take the c1 that's over here. Remember, these are just arbitrary constants that arise from the antidifferentiation process. But if I had a c1 over here, I could just throw it to the right-hand side and then have c2 minus c1. And together, if c1 is an arbitrary constant and c2 is an arbitrary constant, then if you had c2 minus c1, that would be an arbitrary constant. And so we'll just save ourselves the trouble, and we see that this would reduce to one arbitrary constant. This is very important for our theory. We should have one arbitrary constant, and we'll just put it on the right-hand side. Now, this form that we have is called the implicit form of the solution. It's implicit because y is not nicely and neatly solved for in terms of x. In other words, the dependent variable is not solved for in terms of the independent variable. This is called the general solution, or the general solution to the differential equation. This is in the implicit form, but whenever possible, we want to put the solution in explicit form if we can. And so we want to solve for y whenever possible. Now, this isn't always possible, but I think almost all of the problems that you will encounter, it will be rather straightforward to use some algebra and solve for y. So here, if we use a base e exponential on both sides, we get e to the ln of absolute y equals e to the 1/3 x cubed plus c. The base e exponential and the logarithm, a natural logarithm, undo each other here. You just get absolute value of y. Here we can use our properties of exponents. E to the a plus b is the same as e to the a times e to the b. You'll see why I did that in just a moment. And now notice if the absolute value of y is equal to this, then that says that y itself is plus or minus this. And now you see why we wanted to split this e to an arbitrary constant apart from this, is because now think, if c is an arbitrary constant, then e to the c is an arbitrary constant. Matter of fact, it's a positive constant, but it's multiplied by a plus or minus. So if we take these two and consolidate them into one big arbitrary constant and call this d, then we get the explicit form of our solution, which is y equals d e to the 1/3 x cubed. Here, d is an arbitrary constant with the only stipulation that d cannot be 0, because this could not be 0, and then we're taking plus or minus that quantity. This we would call the explicit form of the general solution to the differential equation. This is all of the functions that satisfy this differential equation. Now, geometrically, notice what this is. This is not the graph of a single function, but this is a graph of actually infinitely many functions. This is an infinite family of solutions because it has this arbitrary constant d in here. So what I did is I just sketched some solutions of this. I sketched several of these curves for various values of d. And I didn't sketch infinitely many of them, but I sketched a handful of them, and you can see that we get this family of curves. This is a very important conceptual idea to have solidified in your mind, that the solution to this first order differential equation is what we call a one parameter family of solutions, or a one constant family of solutions. It has one constant in it. And that gives us the graph of infinitely many curves here in the xy plane. And all of these curves are all solutions to the differential equation. So we actually found infinitely many solutions. They were not random, but they all came from this solution just by varying the constant d. Now, another thing that you'll see in the homework is, what if we want to find the one member of that infinite family which satisfies the condition y of 0 equals 2? So geometrically, this just means out of all of these curves, I want the one and only curve that happens to pass through the point 0, 2. What curve is that? Or algebraically, when we look at this, we're saying, which one of these members of this family, what do I need to choose the value d to be in order for this to satisfy the condition y of 0 equals 2? This is called an initial condition. So that what we do is we start with the general solution. We apply the initial condition, so we just evaluate y at 0, so we get d e to the 1/3 times 0 cubed. We set that equal to 2 because that's the value of our initial condition. And then we solve this resulting algebraic equation for the unknown d. Now here, the arithmetic is very simple. E to the 0 is 1, so we get d equals 2. That was just a coincidence that the d value happened to be the number that was sitting here. Sometimes it is, sometimes it isn't. But don't stop here. This is not your answer. Your answer should be return to the general solution and and substitute in the value of d that you found. So we want to substitute in d equals 2 here. And notice from this many members of this family, we've selected one member, the one with d equals 2. And that can be seen graphically over here. The one in red, the curve in red highlighted, is the one that passes through 0, 2. And that's the one member of the family that solves not only the differential equation, but the differential equation together with this initial condition. And just for a little jargon here, if you have a differential equation like we did here, just this differential equation, we got the general solution to that differential equation as a one parameter family, a family with one constant in it. If we have an initial condition, then we pluck out one member of that family. We solve for d here, and we find the one member of that family. And if you have a differential equation together with an initial condition, we call that together an initial value problem, or IVP for short. So this is the solution to the initial value problem, which was our differential equation, together with this initial condition. Notice if I gave you a different initial condition, even with the same differential equation, that changing this would change the value of d, which would change the curve. So as the initial conditions change, the value of the constant changes, and it generates different particular solutions to those initial conditions. So that was an example of a separable differential equation. You can see why it's called that. We separated the variables multiplicatively, and then we anti-differentiated both sides. But beware, not all differential equations are separable. For example, this relatively tame-looking differential equation, dy over dx equals x plus y, is not separable. You can try and see that you will not be able to totally separate all of the y pieces from the x pieces. In fact, an equation is separable if you can rewrite it in this sort of form for some function f and some function g, and sometimes you can do that and sometimes you can't. Everything that we're going to see in 9.1, though, is separable. Now, a very popular application of this theory here, or this topic of separable differential equations, comes from population models. So consider the standard population model, which says that, and you saw these in Calculus 1, it just says that, suppose that we're modeling the growth of a population, and it could be people, it could be bacteria, it could be rabbits, it could be deer, it could be fish in a lake, it doesn't matter what the population is. But let's suppose that we're going to model the population as follows. The rate of change of the population is directly proportional to the population itself. So the more deer that there are on the island, the faster that they're going to reproduce. The fewer deer that are on the island, the slower they're going to reproduce. So the differential equation here, if you just translate this sentence into a mathematical sentence, the rate of change of the population, so I'll take P to be population, T to be time, so T is my independent variable, P is my dependent variable. If we just write the differential equation, we get dP over dt, the rate of change of the population, is directly proportional to, so that means is equal to a constant times the population itself. Furthermore, if we had the initial condition in a real-life scenario, if you were going to model something like this, you would need to know what the initial population was at the start of your experiment. So we would say that the population at time 0 is some given number or known number, P naught. So here, P is population, T is time. K is not a variable. It's a constant of proportionality. When K is positive, you're going to see that we'll get growth. When K is negative, we get decay. So in case you had a population that was dying off instead of growing, then that is modeled by a negative K, and then P naught is the initial population. Notice this is the differential equation. This is the initial condition. When you bundle these together, you get an initial value problem. So let's solve this initial value problem, and we'll do that first by solving the differential equation. So let's start with the differential equation. dP over dt equals Kp. We want to separate all of the P components from the T components. K is just a constant, so it doesn't matter which side it ends up on. So we'll divide both sides by P and multiply both sides by dt. We'll anti-differentiate both sides. This is again a natural log of the absolute value of P. This would just be a Kt plus a constant. We should only have one constant of integration. This is very important. This is the implicit form. We want to put it in explicit form. So we'll hit both sides with a base E exponential. We get this. E to the ln of absolute value of P is just absolute value of P. We'll use our properties of exponents again to decompose this into this. We can drop these absolute values as long as we pick up a plus or minus sign. And now let's consolidate this e to the c, which is an arbitrary positive constant, with the plus or minus. We'll rename it d, and now we get p equals d e to the kt with the stipulation that d cannot be 0. Or if you really want to write that so that it looks like a function, population as a function of time, you get p of t equals d e to the kt. This is the general solution to the differential equation, and it is in explicit form. Notice this is a one-parameter of family of solutions. D here is the constant that came about as a result of the integration. Remember, the k is a number that we would know that it would be embedded in the differential equation itself. Okay. Finally, let's apply the initial condition to determine the constant d. So we'll just take this general solution, we will evaluate it at t equals 0, and we'll set the result equal to p naught because that was our initial condition. Notice this gives us an algebra equation in the unknown d. D here is p naught. So we'll just go back to our general solution. Wherever we saw a d, we'll put a p naught. We'll highlight this as our final answer. This is the solution to the differential equation and the initial condition. In other words, it solves the initial value problem. Now stare at this function for just a moment. Notice we haven't made any claims yet about the constant k. Note that if k is positive, that these would be growing exponentials. Think of an e to the 2t, an e to the 3t, an e to the 100t. These are growing exponentials, so the graphs would look like this. On the other hand, if k were a negative number, like e to the minus 2t, e to the minus 0.1t, and so on, that these would be decaying exponentials. They would look like this. They're in decline. So that's very important. Notice the signature of the growth constant k, or the constant k. It's only growth when k is positive, and it's decay when k is negative. Affects both the form of the solution, but also it affects what the graph looks like and the behavior of the solution. So that's very important. Let's look at an example. Suppose a bacteria is growing in a dish and obeys a standard exponential growth model. At time t equals 0 hours, there are 100 bacteria present, and at time t equals 2 hours, there are 120 bacteria present. Let's write down the initial value problem modeling this scenario. Let's find the numerical value of the constant k. They told us that this is growth, so we're looking for the numerical value of the growth constant k. Let's solve for the population as a function of time, and then once we have our hands on that, we'll be able to answer basically any question that you'd want to know about this population. For example, we could say, how long will it take until there are 500 bacteria present? Okay, so let's begin by writing down, not solving yet, but just writing down the differential equation together with the initial condition. So the differential equation, since it's a standard exponential growth model, looks like dp over dt equals kp. P of 0 equals 100. We don't know k yet, but we know that there's some constant k that goes there. Now the solution to this, we already know from above, the solution to this is p of t equals p naught e to the kt. We know our p naught is 100, so we'll put that in. This feels a little different than before. We don't know this value of k here. We just have to be patient. But notice they gave us an extra piece of information. Not only did they give us an initial condition, they gave us a second observation. This second observation, as long as you have two observations, and you always have to have at least one, because this is the initial condition. So this isn't the initial condition, it's just a secondary observation. As soon as you have a secondary observation, you'll be able to determine the value of k, and I'll show you how. So let's go back. We have so far p of t is 100 e to the kt. We're looking for the value of k. Let's plug in our second observation. We know p at time 2 is 100 e to the k times 2, and then we were told that that equals 100. Now if you stare at that equation for a moment, that is an algebraic equation in the unknown k. So just solve for k. Divide both sides by 100, apply a natural logarithm to both sides, and divide both sides by 2, and you get k is ln of 1.2 over 2, and that is approximately 0.0912. So now we found the numerical value of k, and so part C asked us to write down the solution, write down the population as a function of time, and so all we need to do is return to what we already had and plug in our k. So our k was 0.0912, and this tells us the population at any time t. We could graph that, we could take its derivative to find the rate of change, we can answer all sorts of questions about it. Finally, they asked us to find how much time it would take for the population to reach 500. So we just want to set the population function equal to 500. Well, the population function is this, we just said. This is now an algebra equation in the unknown t, so just divide both sides by 100, apply a natural logarithm to both sides, and divide by both sides by 0.0912, and you get that t is approximately 17.65 hours that it will take for this bacteria to reach 500, population of 500. Okay, to summarize, let's look at a comparison of an exponential growth model and an exponential decay model, and I want to point out something that a little bit of a difference. I think it's compared to how I'm explaining things compared to our book. Both are correct. I just think that there's a little bit easier way to compartmentalize this in your mind that will make it where you have less mistakes when you're memorizing things. So the exponential growth model looks like dp dt equals kp. Here the k has to be positive. The initial condition is p of 0 is p naught. So this is all standard. We know that our solution looks like this. We did this above. We know that the graphs are exponential growth, so they start off at p naught and they grow like exponential functions. And then one important thing is to calculate the doubling time for an exponential growth model. That's just the amount of time it takes for the population to double. So we would do that, and they do this in the text, but all we would do is take our solution, and if we wanted to find the time when it was twice as big as it was before, we would just say, set this equal to 2p naught, and then solve for t, and this is the t that you'll get. The doubling time is the natural log of 2 over the value of k. And notice the k here is positive. So all this is standard. This is exactly what the book does, exactly what I do. Now here's the difference. For an exponential decay model, the book writes their model down like this, so it looks the same, but you have to remember that the k here is a negative number. That's totally fine, it's totally correct. What I prefer to do is just make it really, really explicit and I follow what's in the green. And what I do is I let the whole world know that this number on the front of my p is going to be a negative. And so I write the negative in my model. So there's a minus here, and then my k is positive, which will make this total number negative. What's important is that the number on the front of p is a negative number. Notice this accomplishes that, and this accomplishes that. It's just two different ways to write it. Now, when you do write it this way, the reason I like to write it this way is because when I solve, notice solving this and solving this is exactly the same. Wherever I see a k, I just put a minus k. I like the look of this because I can see the decaying exponential. It reminds me of the geometry. It reminds me that the population is decreasing with respect to time, and this is the way that I prefer to write it. Now, an exponential decay model doesn't have a doubling time, but instead it has a half-life, the time that it takes for the population to be cut in half. And it turns out if you write it this way, the formula for half-life in a decay model is exactly the same as the formula for doubling time in a exponential growth model. So using my formulation above, this is the formula that you would use. And then you just get to keep the same formulas. You remember one thing. The book explains it a little bit differently. If you write this as without a minus, it changes the look here and it changes the formula here. I would recommend that you follow the green. My teaching experience says that students tend to retain that information better when they're following the green. However, if you're looking in the textbook and the explanations that they give, and if it looks a little different, this is how that you can reconcile those two things. As a final example, you might see something like, suppose the amount A of a radioactive substance at time t obeys the differential equation dA dt equals negative 0.02 times A. Find its half-life in years. So we'll assume here that t is in years. And notice that they gave us the differential equation model. To find the half-life, the initial condition doesn't even matter. What really matters is the growth or decay constant. In this case, it is a decay model because we have a negative k value here, the negative number on the front of our dependent variable. And the k here is just this number. It doesn't have the minus. Remember, go back to the model. The k is just this number without the minus. When the book does it, they write it differently, but if you're going to follow the green, it's just the k without the minus. So I'll pick my k here, peel off my k to be 0.02. The half-life formula is just the ln of 2 over my k. It's the ln of 2 over 0.02. That comes out to be about 34.68 years.